Hi, I'm Sarah McAllister, and today I'm going to be talking about my project Kangaroo caching billions of tiny objects on Flash. And this is work with a bunch of other people here at Carnegie Mellon, and then our collaborators at Facebook and Microsoft Research. So in Kangaroo, we're focusing on caching tiny objects. And the reason we're focused on tiny objects is because they're prevalent and they're an underserved use case. And so where do we see tiny objects? Well, tiny objects are apparent in the social graph, such as Facebook's social graph, which has edges that average around 100 bytes that connect any friends or any posts people make. We also see tiny objects in IoT metadata. For example, at Microsoft Azure, all sensor metadata averages around 300 bytes. And then we also see it in things like tweets or other text data. For instance, Twitter tweets average less than 33 characters on average. So with all these tiny objects at massive scales, we want to be able to serve them at scale to various applications. And one of the ways we do this is by caching massive amounts of data. And so when an application wants a tiny object, what will typically happen, it'll send that request to a caching layer. The caching layer will return the object if it's a hit, has a hit. Otherwise, on a cache miss, the request will be sent back to database layer. And so the caches here have two main goals. They want to lower the average latency of the entire service, and they also want to keep load off the backend services. And to really have a caching layer that's effective at scale, these caches need to be really big. And one way to make them really big is to use Flash, because it's 100 times cheaper per bit, so you can have much larger caches for the same cost. And so at scale, a lot of companies deploy Flash caches. So with Kangaroo, we're really trying to solve this problem where we need to cache billions of tiny objects on Flash. And if you look at the prior work of caching tiny objects on Flash, they either have this problem of having too many Flash writes or a large memory overhead. And either way, you're going to waste money on your cache. So Kangaroo allows us to solve this problem while reducing misses. And we reduce misses by 29% over comparisons, and while keeping writes and memory pressure under production constraints. Kangaroo is open source and it's integrated into CacheLib, which is Facebook's caching engine that they use in production and is open source and can be found at cachelib.org. So now that I've introduced the problem that Kangaroo is trying to solve and a little bit about what Kangaroo does, I'm going to be talking about the challenges of caching on Flash. Then I'll be moving on to how we can cache on Flash while minimizing DRAM overhead, which will lead us into Kangaroo's design and finally the results. So when we think about caching on Flash, we have all the challenges that you have with caching on DRAM, but we have the additional challenges. And so Flash allows us to have cheaper caches, but Flash devices also have this problem of having limited write endurance. There's only so many times you can write data to Flash before that Flash device will wear out and no longer work. And since caches are constantly changing what data is in the cache, this write endurance becomes a really significant factor that we have to take into account when building caches. In addition, Flash caches have to write in at least 4 kilobyte blocks because this is the minimum read-write granularity of a Flash device. And this write granularity is bigger than the objects that we're actually looking at. And so to solve both of these problems kind of in conjunction, most Flash caches use a log structured cache. And so a log structured cache, similar to a log structured file system or another log structured base store, will take an object and buffer it in DRAM. And this is so that we can have one really large write to Flash. So once your buffer is full, we write the entire group of objects to a segment in the log and place enough metadata in a log index to be able to find them again, since objects can end up anywhere on Flash in our circular log. Eventually, these objects will have to be evicted, and usually they'll be evicted all together as a segment as they're written in. And so the big advantage about this, of using a log structured cache, is that we're buffering our writes in DRAM so that we have a really small overhead when we're writing them to the log. And so our buffered writes minimize the number of writes to Flash, and we don't wear through our Flash devices quickly. The downside is that there's a full in-memory index, since an object can end up anywhere in the circular log on Flash. And so this full in-memory index becomes a large problem when you have tiny objects. As I said earlier, we need to cache tiny objects because it's a common application use case. But if we look at the overhead for tiny objects, when we have a full in-memory index, we start to see a problem. So if we look at just an object metadata overhead of 30 bits per object, when we have a reasonably sized object, not a tiny object, we can see that there's not a lot of overhead. And so we can see here that the 4 kilobyte object has a 0.09% overhead with 30 bits per object of metadata. And so that's pretty reasonable. But if we go to 40, 100 byte objects, so taking up a little bit less flash capacity if this was on flash, we see that we have a 4% overhead for all of these objects on flash. And so even at 30 bits per object, which is the best that we see in literature, we have a large overhead. And so if we scale that up to a full flash cache, which might be 2 terabytes at a smaller size, we can see that we'd have 75 gigabytes of memory overhead just to be able to index all of the objects on flash. And this doesn't include any overheads or any uses of memory, such as having a DRAM cache or any extra metadata you want to keep track of what objects receive hits or anything like that. So that would add to this memory overhead and really get us away from the whole goal of using flash in the first place, which is to not pay for large amounts of memory. All right, so if log structured caches have a large DRAM overhead, what can we do to reduce that DRAM overhead? And so it turns out you can design your cache to really lower the memory overhead. And one way to do this is to use a set-associative cache. And so if we have a key coming into a set-associative cache that we want to find, we hash that key to find what set it's in, read that set off flash, and search for the key. And so this is really nice because we just need a hash function in order to find where an object lives, and we don't need to keep any in-memory index. If we look at what happens on an insert, it's really similar. We still hash the key to find what set it's in. We then read that whole set up off of flash, insert the new key, evicting some old objects to make room for the new object, and then rewrite the entire set back to flash. So as I said, the advantage of this is that there's a really low memory overhead. We might keep Bloom filters around to optimize the read path and get better performance on misses, but otherwise we don't need any memory. The downside, however, is that there's a large write amplification, and we're going to define write amplification as the number of bytes written over the bytes requested. And so here we have to write an entire set, which is 4 kilobytes, for each 100 byte object that we want to insert. So our write amplification becomes 40x, which is much higher than your optimal write amplification of 1x, and it means that we're going to be wearing through our device a lot quicker. And thus the device might not last for the device lifetime. So if we look at prior work as a whole, we can see there's really 2 axes we've talked about. And here you can see them on the y-axis, we have memory overhead. On the x-axis, we have write amplification. So with the log structured cache, we have a high memory overhead because we have to have that in-memory index, but there's a low write amplification, close to optimal. For a set-associative cache, there's a really low memory overhead because we potentially only have those Bloom filters if we want them. But there's a really high write amplification because you have to write an entire set, which is a minimum 4 kilobytes for every new object you want to insert into the cache. So neither of these options really get us to where a production system can minimize the cost, which is with a low memory overhead and a low write amplification. And that's where Kangaroo comes in. Kangaroo allows us to span this trade-off between memory overhead and write amplification and find a point where we're happy with our production system and the costs that go into maintaining that production system. So now that I've talked a little bit about the problems with prior designs and what Kangaroo allows us to do, I'm going to talk exactly about how Kangaroo does this. And so overall, Kangaroo has 2 main parts. It first has KLog, which is a log structured cache. And so it has an index and then a circular log on flash. And this is going to be a small amount of flash, say 5 to 10%. And then once an object gets evicted from KLog, it's going to get moved to KSet. And so KSet's a set-associative cache that's going to take up the remainder of the flash capacity. And as we'll see, it allows us to have a low memory overhead since this takes up most of flash. So how does this actually work? So if we look at inserting an object into Kangaroo, such as this blue object here, it's first going to get inserted into KLog. And we're going to do this through a buffered write, just like any other log structured cache, which will allow us to minimize the number of writes that we do to insert this object. and it's going to get an entry in the index so that we can find this object again. Now, eventually, we're going to have to evict objects from KLog, such as this yellow object here. So when we do that, we're going to want to write it to KSet. But before we write it to KSet, we're going to look through KLog to find any other objects that map to the same set in KSet. And so in this case, the pink object maps to the same set in KSet as the yellow object. And so we're going to move both the pink and the yellow object. And we do this so that we're amortizing the writes to KSet over multiple new objects. So if we look specifically at that part, we can see that when we rewrite KSet with one new object or two new objects, we're still rewriting the same amount of data. We're still writing the 4 kilobytes for sets of 4 kilobytes. However, now we're doing it over 2 new objects rather than 1 new object. And thus we can halve the write amplification to KSet by writing 2 new objects, such as the pink and the yellow object, instead of just a yellow object. And so KLog allows us to have more time to find these set collisions by dedicating this 5 to 10% of flush to the log. And thus, when we find these set collisions, we can amortize the write amplification. And we can do this with even a very small KLog. So you can see here on the graph, we have a y-axis. That's the percent of the objects that have a collision in KSet when they get moved from KLog to KSet. And on the x-axis, we have the KLog as a size as a percentage of flash. So you can see even with a 5 to 10% KLog size, we have a high probability that we're going to get a collision from 50 to 75%. And so even at a small KLog size, we can get a large number of collisions, which means we can lower our write amplification over a naive set-associative cache design. And so this allows Kangaroo to span trade-offs. The larger KLog is, the more collisions that'll occur, which means the lower write amplification, but the higher memory overhead Kangaroo will have so that we can index that larger KLog. And so as you can see, we can span this memory overhead versus write amplification trade-off that we had earlier. However, even with this design, we don't quite reach the production system desired goal. And so now we ask, can we move the Kangaroo curve farther to the left? And so to do this, Kangaroo implements something called threshold emission. And the key insight about threshold emission that we haven't talked about is that in caches, you can choose what objects you want to discard. This is because objects are already on some type of backing store, so they don't need to survive in the cache. And so specifically with threshold emission, we're going to choose which objects to discard based on their write cost. So let's say that we want to implement a threshold emission with a threshold 2. So with threshold 2, the pink and the yellow objects have 2 objects. So they're going to get moved to KSet. However, the blue object here doesn't have any partner in KLog to get moved to KSet. So its write cost is going to be a lot higher. And thus, instead of writing it to a set in KSet, we're just going to evict it. We're going to throw it away, put it in the trash, and lower our write costs that way. And so this allows us to shift that curve to the left and improve our write amplification for the same memory overhead and reach that production system constraint. However, this doesn't come without causing other problems. One thing that we haven't talked about so far is this other trade-off, this misratio trade-off. Because discarding objects, you can imagine, can lead to misratio losses. And so here on the left graph, we have the same graph you saw earlier. And on the right graph, we have misratio on the y-axis and write amplification on the x-axis. So the log structured cache and the set-associative cache have very similar misratios because they use similar eviction policies. And so you can see that they just are different on the write amplification axis. Whereas Kangaroo is throwing out objects using its threshold emission policy. And this allows us to reduce the write amplification. So as we have a lower write amplification, the misratio is going up because we're potentially evicting popular objects from the cache. So this isn't ideal because part of the reason of having these caches in the first place is to keep load off the backend services. And we keep load off the backend services by having a low misratio. So how can we improve misratio in Kangaroo? Well, one easy way to improve misratio in Kangaroo is to have readmission to KLog. And so here we can see that we have this blue object, and there's a chance that it's a really popular object that we're throwing away that would get requested again and cause us misses. So instead of just throwing it away, we're going to ask a question of whether it's popular. And if it's not popular, we're going to do the same thing that we did before and throw it away. But if it is popular, we want to keep it around. However, KSet, moving into KSet, still has a really large write cost. So instead of doing that, we're going to buffer it back into KLog so that we keep it around and potentially allow it to have more time to find a partner into KSet while not incurring the high write costs that moving it to KSet right now would have. And so this allows us, as you can see on the right graph, to reduce our miss ratio, to reduce the detriment that threshold admission had on our miss ratio. However, our miss ratios still aren't great, and this is partially because all of these caches right now are using a FIFO eviction policy. And the reason they're using a FIFO eviction policy is because it can cut down on the number of writes that you have to do and requires little metadata overhead. However, the problem with using FIFO eviction is that you don't get a very good miss ratio. And so this leads us to trying to have a better eviction policy in Kangaroo that can allow us to lower our miss ratio even more with a low memory overhead and without incurring extra writes. And so to do this, Kangaroo uses what we affectionately name RRIParoo eviction. And so the problem here is that we have two groups of objects. We have objects coming in from KLog, and then we have objects that already exist in the set. And so we want to retain the most popular objects out of both of these groups and rewrite them to the set. But we need to be able to choose which objects are most important without having a high memory overhead. And so we do this using RRIParoo, which is a modified version of RIP, which is a processor cache eviction policy. And so that uses a history of what objects have been requested to keep recency information about these objects and set an order in which they should be evicted. The big advancement in RRIParoo over a basic RIP design is that we can use RRIParoo to have 3 bits worth of information around all of these objects while only keeping 1 bit in DRAM per object for every object in KSet. And so we essentially do this by keeping the 3 bits of worth of information on flash, and thus only need 1 bit of information in DRAM to have a very effective eviction policy. And I encourage you to look in the paper for more details. And so with RRIParoo, we can improve our miss ratio. So you can see on the right graph, Kangaroo's miss ratio comes down using RRIParoo. And on the left graph, the memory overhead is only a little slight bit. So the Kangaroo line only goes up a little bit. All right, so I've talked a lot about Kangaroo's design and optimization, but let's see how it actually works in practice. So as you can see here, we have a graph where on the y-axis we have miss ratio and on the x-axis we have days. So we ran Kangaroo and a set-associative cache and a log structured cache on a 7-day trace on a 2 terabyte flash drive. And so the worst performant out of these 3 options was the log structured cache. And this is because it's severely DRAM constrained under our setup. And this is even with being generous to log structured cache in terms of DRAM. But it just can't index the whole flash capacity, and thus the miss ratio is not very great. With a set-associative cache, it's not as bound by the DRAM capacity, but it's write constrained, so it can only do so well in terms of miss ratio. Whereas Kangaroo is able to span both the DRAM and the write rate constraints, and so it allows us to have a 29% miss reduction over the set-associative cache and an even larger miss reduction over the log structured cache. Because it can span both the write amplification and the DRAM constraint while also implementing a better eviction policy to allow it to have a better miss ratio. So all of that was under one constraint. And so one of the other things we wanted to do is show how Kangaroo performs under varying constraints. And so first we're going to look at what happens if we vary the DRAM budget. So these results are going to be in simulation so that we can run under a bunch of different constraints. And so on the y-axis here, you can see miss ratio. And on the x-axis, you can see DRAM in gigabytes. And the production constraint we had on the previous graph is the vertical black line. And so we can see that the set-associative cache is not very affected by DRAM. It has a slightly larger DRAM cache the more DRAM you add to the system, but this does not make a huge impact on miss ratio. However, the log structure cache is very impacted by DRAM. when it has less DRAM, it just can't index as much of Flash, so the capacity of the cache is much smaller, but it does better the more DRAM it gets. Kangaroo is better than both the log structured and set-associative cache over the entire DRAM budgets that we present here. And it's also minimally affected by DRAM because it can adapt to less DRAM. Even on the right side, where the log structured cache starts to approach Kangaroo, Kangaroo keeps an advantage over the log structured cache. And we see this as we increase DRAM beyond the point of this graph. And so the other constraint that I want to look at here is varying the write rate. And so before we had a write rate that corresponded to 3 device writes per day, and you can see that production constraint on the black line here. And again, like the last graph, the y-axis here is miss ratio, and the x-axis is write rate. And so as we vary write rate, we can see that the log structured cache doesn't change that much in terms of its miss ratio. This is because it's still really DRAM constrained. So unless you have a very, very low write rate, it's just going to be constrained by how much DRAM is in the system. Whereas Kangaroo and the set-associative cache both are more constrained by write rate. The set-associative cache performs worse than Kangaroo across all write rates because Kangaroo has various optimizations, as I said earlier, to amortize writes and to have better eviction policies. So it performs better than the set-associative cache. For the most part, it also performs better than the log structure cache. On the left side of the graph, the log structure cache is better. This is partially because we didn't run Kangaroo with larger logs, so that it approaches that log structure point. So overall, if we look at Kangaroo, Kangaroo allows us to cache billions of tiny objects on Flash. And it does this while keeping the write rate within bounds for the device lifetime by amortizing the write costs. It has a low memory metadata overhead, and it allows us to decrease misses over other competitors by 29%. It also responds well to changes in system parameters. I encourage you to look at our paper for more about how Kangaroo's optimizes DRAM and its partition index for KLog, its optimality on the Twitter traces, and our test deployment in a shadow production setup at Facebook. Finally, I'd like to thank the CacheLab team at Facebook for all their help on this project, and for both Facebook and Twitter for sharing traces with us.